morning, everyone. Today, what I'm going to talk on actually not on commercialization. It's purely on my pure research, theoretical research. What I will do is, I think carbon nanotubes have been here for about 25 years, not too long ago. Then how to make use of these carbon nanotubes into composite materials. That's my topic today. We have done it, I think, in the past 10 years, and we have a lot of results on this. So I just present some of the results today, and I think we can share. And I will give maybe half an hour talk, and I'll leave about 5 to 10 minutes for question and answer. I think there will be hopefully created some interesting question from you. You look at carbon nanotubes. Let me go through what is carbon nanotubes, how it behaves, then before we use it for composite materials. You look at carbon nanotubes. That was discovered, I think, reported by Ijima, actually Dr. Ijima. He published a paper. Thank you. He published a paper in 1991 in Nature, actually. That's actually, to my knowledge, that wasn't the first person who discovered the carbon nanotubes. I think that was discovered in 1960 by Russian scientists, but that wasn't published at that time. So Ijima was the first time, I think he published in Nature and created a lot of impact. So in this publication, I think he lists down a few things actually. He said that carbon nanotube can exist in certain patterns. There can be a single wall. It can be, double wall, or it can be multi-wall actually. That's what he reported in the paper published in Nature. Then, he further says something actually in the publication. He said, okay, you look at under TEM, the structures of this carbon nanotube, it can be zigzag arrangement, it can be chiral or armchair. There are 3 types of them actually. And what do we usually use in our today actually when we make into nanocomposites? We are using armchairs, more stable actually type of carbon nanotube. That's why we use it for our applications. We don't use the other 2 types for carbon nanotubes. And the publication also raised a very big concern actually, is that stiffness is extremely high, equivalent to diamond. That's what was reported in that paper. And he said that the strength is 100 times more than steel. You see, I'm trained in civil engineers, as a civil engineer. We know that steel, we use a lot of steel in our building, in our design actually. But you look at this, it's 100 times more than steel. Can we use it for our, civil engineering applications? That's the first thing I will look at that. And I'm going to give you some simulation that was done, I think, about 15 years ago. But it was published in, I think, in a Physical Review B. And this is a paper. Actually, I put out here, and I show how to use the molecular dynamic simulations. That was the first time, I think, we simulate using MD in the world. First one, we have done that. And how the MD can simulate this carbon nanotube. You look at atoms, all the atoms in the carbon nanotubes, how it buckles when you apply a compressed load. It's not really similar to what the conventional tube. We look at our steel bar or tube. When you do a compression, normally we'll do it, they will buckle at the center. But you look at this carbon nanotube, it doesn't behave in such behavior. It's very funny kind of behavior actually. So, so the conclusion is, if you look at it carefully, initially they keep in cylinder, it still remains cylinder before deform into 3 fin. You see, it go into 3 fin kind of deformations, and finally led to a plastic collapse. It will collapse finally because when you compress further and further, it go to plastic deformations. Finally collapse. That's how it behaves in this single carbon nanotubes. And how about when you apply bending and torsion. So as trained as civil engineer, you always think torsion, bending, twisting and sort of thing actually. So when you apply bending, what happens to bending? We apply at two ends. If this is a narrow tube, apply forces at two ends to make it bend. So that's how it behaves actually. We study a 10 means armchair carbon nanotubes with a length of 12.56 nanometers. When we put two ends, subject to a torsion actually, subject to a bend moment actually, bending moment. And we did a simulation by both ways actually. We have employed two methods. The first method we use continuum methods. When I think those material scientists, they use higher Cauchy bond rule. That was a continuum mechanics actually. We use that methods to simulate these nanotubes subject to bending actually. And also we have done this molecular dynamic simulation. We have to make some comparisons, see what happens if the continuum mechanics and molecular dynamics, what happens when we do this kind of simulation. Does it tally with the result we expect to get actually? You look at when we use the continuum theory, the bending angle at that is about 24.5 degrees using continuum theory. And we do a molecular simulations, we get about 25 degree bend angle. So we said as both theory is quite good actually in this way. How about torsion? So we also have done the torsion. Torsion means if you have a bar, both sides you give a rotation to that. And you look at that. The twist angle, the twisting angle is about 28 degrees. But molecular simulation give you a slightly higher, about 30 degrees. So it's not too far away. So I will say that those simulations is acceptable. Now, I also mentioned it's not only single wall. You have multi-wall carbon nanotubes. What happened to multi-wall carbon nanotubes? We have done a simulation on this. When you have a four wall, then you have tube by tube, inner tubes. There are four tubes within tubes. So we get from a very small 5-5 armchair, 10-10, 15-15, 20-20, back into a four-wall carbon nanotubes. And when you pull it, subject to tension, what happened to that? We have done a simulation on this number of years ago. And you can have a look. Yes. You see, when you pull it, subject to tension, there's the layer of finally each layer of fracture actually. And you don't know which part it fell first actually. It doesn't see anything. But if you look at that carefully, we have done the analysis carefully. We look at the overall fracture. You see, if this is overall, the first layer, you look at the first layer first, the outer layers, it get fracture first, and it followed by second layers, third layer, finally the inner layer. So if you have a bar, if you have bar into a bar, when you pull it, it doesn't behave in this way actually. I think it doesn't fail in the outer to the internal actually. It fail at the same, almost the same time if you use a steel bar. Look at that. So it's behave very, very different from our conventional methods. This is another finding we have found some time ago. And how about you put these nanotubes under temperature, different temperature. You look at this. We have done these molecular simulations. We subject to, we start with 300 K, K means Kelvin at that temperature, to 1,000, to 2,000, 3,000. So the nanotube they will deform at certain stage. Now, you look at all this. When the nanotube will fail, where is the critical temperature that will make the nanotube fail? So you go further. The critical temperature make the nanotube fail is about 3,489 K. Why we do this? I think we have done this. There's a lot of people, commercial people, they want to use it for electrical application, chips design. They need this simulation. We have done it for them actually. At that time, I think about 5-10 years ago, we have done that. For them actually, we show them the critical temperature is about 3,000 degrees on that. Then they are not happy. How about we have more wall. What would that end up? So we also done actually some simulation. Okay, you look at 2 wall, double wall nanotubes. We have 5, 5, and 10, 10 nanotubes. Put them together, subject to the same temperature, 300, 1,000, 2,000 temperature. But the result end up when you have 2 or we can double wall carbon nanotubes, the critical temperature is much lower. It's around 2012 kelvins. When you study a previous slide, for single wall carbon nanotube is over 3,000 kelvins, and for double wall is 2,000. What would happen actually? You see, as a civil engineer or mechanical engineer or whatever, we believe when you have more wall, it should be better. It doesn't happen that way in these nanotubes. The reason behind is when you have 2 walls, is it single wall? When you subject to heat, they vibrate. You do not need to hit on the other wall. And you look at double wall, the inner tubes, the 5 nanotubes, it vibrates, very fast, subject to temperature change. So when it vibrates very fast, it hit on the outer wall, so they break slightly easier. That's happened to nanotubes. It doesn't happen to our steel. If you look at our civil engineers as an application of steel, actually. So this is another very different behavior. Now, we see all the mechanical behavior of carbon nanotubes. How are we going to use it? How can we use this carbon nanotube into our composite materials? That's what I will do. You look at this actually. When you put this, a lot of implications. A lot of people reported that. When you put CNT into polymer matrix, that improve the mechanism, electrical thermal properties for resulting nanocomposites. I show you some of the testing. You look at the Chen research group. They have reported a paper in Applied Physics Letter in year 2000. They said that they did a tensor test. They said, the modules increased from 1.2 kilopascal to 1.62 kilopascal for polystyrene and 1.69 for composite filled with 1% weight short or long nanotubes. You see, that increased from 1.2 to 1.6 or 1.2 to 1.69. So they found that it's interesting. So when you put in a bit of nanotubes, the strength increases. Now, there's another paper published by their research group, also in the Physics Letter, in years 2002. They reported that for multi-wall carbon nanotubes, you put them both in polyethylene alcohol and polyethylene carbonate, that increase in module from 7 GPa to 12 GPa. From that. And you need only to 8.6 volume % of this multi-wall nanotube in this polyethylene alcohol. But the increase, if you put 4.8% of this multi-wall into this polyethylene component, that increase from 2 kilopascal to 5.6 kilopascal actually. So you see, there is another experiment that proved it, that increase in strength. And finally, when there's a report, actually, they published in Polymer in 2002. They reported that for mixture of polycarbonate and CNT, 2% of per weight of this carbon nanotube, they cause significant improvement in electrical resiliency and compressive viscosity. So when you found all this, they're all talking about adding a bit of carbon nanotubes that make good of this composite. The composite becomes stronger or become better in kind of applications. So as engineers, I train as an engineer, always think that how are we going to use these nanotubes to composite or to certain structures to make it stronger actually. So I did experiment in making these nanotubes they put in concrete. How to make the concrete stronger, and also how the concrete, when you make these carbon nanotubes, is it a better fire resistant Because in Hong Kong, we are very concerned about when you are high-rise building in Hong Kong, they have 100-story high kind of building actually. We are concerned about the fire resistance actually. We want to make concrete. Nothing wrong. We are trying to make concrete in such a way that they can be fire resistant. Life is precious actually in Asia, so we want to make sure that life is safe in Hong Kong. You stay in highly story kind of hotel or sort of thing actually. So we've done that. But today I'm not going to talk that because I'm going to talk on something making in composites. What we have done, we are going to, in conventional composites, we are using glass fibers, carbon fibers, or keyboards or wire fibers. But how about we reduce that by carbon nanotubes? Does it look better, or is it better, or whatever actually? That's our intention to do that. So we made a few patterns. How about we enforce uniformly enforced by carbon nanotubes, single wall carbon nanotubes? Or we can arrange in the V shapes. So in such a way, you say that functionally created in the V kind of shapes. Or we can have something like, set more at the center, less on the top. We call it O shapes, FGO. And, we can have a cross shape, more on the top and bottom, less at the center. We call it X kind of distribution. We call it FGX. So we try to make this. Of course, I think you can create more kind of arrangement actually, because I think if you work it out, the material property, you can work it out by rule of mixture or sort of thing actually. It's not difficult. So we just make a few and show some presentation. The first test I will do is we have carried out with a student and some of my research group and partner. They have done something on, we do some elastodynamic analysis. When you make a plate, it's subject to load with time varying. What will happen to these composites? So we have created some algorithms. Of course, this is an equation of motions. And we do kind of, we have to get this stiffness and sort of thing in engineering. We all know that stiffness, damping, whatever actually. Okay, we created that. Then you use Newmark beta to do the time integration because you need to move along with time. So we have to do some integration, integrate the time into the deformations. And finally, we can get the equation and find out what is the deformation step by step at every time step. That's what we have done in this kind of slide, in this slide. This is a kind of plate. We selected to do a test actually. And they're subject to the impulse, dynamic load, sudden impulse load on that. We can see that, as I mentioned to you, for this case, we choose X. X means top and bottom, more common nanotubes, center, less nanotubes. Okay, how does it behave actually? You look at it when we subject to different boundary conditions. Different boundary conditions with the four edges. We have semi-supported, we have semi-supported at two opposite edges and two free on the other two edges. Or you can have clamp on two edges and free at the other two edges. Or finally, we are all clamped. We study all the cases, see what will happen to the load, how it behaves. And it end out. All this deformation depend very much on the boundary conditions. The semi-supported have the, the semi-supported, not semi-supported, the SSSF actually, have the largest deformation. Followed by the semi-supported, followed by CF, and final clamp. This is very normal. You look at the structures actually, when you have clamp at four-sided, the stiffness, you imply the force is much larger to the structure actually. When you subject a load, of course, the deformation is much less. That's how it behaves. I think it's very logical according to our engineering mechanics kind of thing. And okay, how about different distribution of functional graded these common nanotubes? We study uniform distributed, the O type of distributed and X type of distributed. See what will happen to that. And we found out, when you have, X type, this is the X type, this is the O type, and this is the uniform type. And we found out when subject to load, the X type, that means the top and bottom more carbon nanotube can sustain more load capacity. So that is good for load carrying capacity. It doesn't mean it's good for others actually. It's good for load capacity. All right. I think the time is go very fast. Okay. You look at when we do the other type, we subject to different type of loads actually. And we also have done some different type of loads and do different type of analysis. I'm going to skip this. I think the time is... You see, today the focus on the conference on smart material and structure. So I, of course, have to do a bit of smart structures actually. And we talk about smart structures. You can have two types, passive or active control. So what today, I'm not going to talk on passive. I will talk on the active control actually. Active control means we are talking about vibration, shifts, and sort of control actually. And this will be focused. And you look at this FA18 jack. This is the fin of the jack. Then put in a lot of piezoelectric materials to damp down, to reduce the vibration arise from turbulence actually. That's what they have done in the aircraft. And you look at this. This is another smart fin. Then what they do is, when you go through very high supersonic flow, it floods. How to control flooding actually? So same thing. They have done the test in the wind tunnel experiment setup, and they put all the piezoelectric and with all the sensors, we test out what happened to that. Can we control the flooding actually? We have done. It's not done by me. It's done by someone actually. I think in the state, very likely. What I will do today, I will give you some of our actual study. We pick the kind of materials, nano-composite materials actually. On top and bottom, we put piezoelectric. And we split into 16 piezoelectric on top and bottom, made as a sensor actuators on top and bottom. And for shape control, we have to pick a shapes, whatever shape we want to pick. But we use a GA, general algorithm, to search the deformation, the maximum deformation on that part actually. This is one of the tests we have done. We know that the first vibration modes for this composite, that's how it behaves. Now, how can we apply the piezoelectric effect that create the desired shapes? What kind of electric voltage we need actually? We have done that actually. So those three design this achieve. When you need to achieve that, you look at the distribution of the voltage. There are 16 piezoelectric, so you have 1 to 16 actually. And you look at different distribution of functional grade material. And we have UD, FGS, and FGO. From this conclusion, you look at the FGO have the lowest frequency. So the conclusion is you look at FGS is bigger. The voltage is much larger UD more than FGO. So conclusion is easier to control vibration if CNT are located at the neutral plane. That means you want to have a control, better control. You better put nanotube more at the center, actually, less on the top and bottom. That's our study. And now, this is only the first mode. How about you start the fourth mode, the 2-2 modes. We also do. We know the fourth mode, the 2-2 modes, how it look like. We also use the GA to find out the deformations. How, to achieve that. We have done that. Now, for 3-1 modes, anti-symmetric mode, we can also, did some calculation and achieve what we want actually using the algorithms. Now, for closed loop control, we are not looking at the voltage. We are looking at the gain how much is gain in that closed loop. And also we have studied different materials. So we have UD, FGX, and FGO. Different kind of different. So the conclusion now is very similar to what we have for the open loops. That means the FGO is easier to control than FGX in this respect. How about when we study with different patches as actuator and sensor for vibration control? This is how the result look like. We put different CNT distributions with CNT, FGS, FGO, and UG types. If you look at the result, subject to forced vibration and free vibrations, the result end now is the vibration amplitude is FGS is much less than UD and FGO actually. It means that FGX is the stiffest between the three types of materials. If you put the material on top and bottom more, it's stiffest actually. The split becomes stiff, much stiffer than others actually. So it's effective to vibrate if more CNT are located near the surface. Because it's stiffer actually, it's easier to control. That's what, it's more effective to do that. This is the same thing. I'm not going to. This is when you use the velocity feedback control to do a calculation on that actually. We end up, when you look at the free vibration type, without control, you know that the dotted line are without control. With the control, we can see that initially the amplitude is quite high, finally it damped down to the end, so it can be controlled. And similarly, for the forced vibrations, this is the uncontrolled part, the dotted line, and the solid line is controlled part. So it's well controlled if you use velocity feedback control on this piezoelectric plate. This is an interesting one actually. We picked two modes as a control actually. We picked the mode 1 and mode 2. Then we try to find out where are the best location to put the piezoelectric materials in. We put three cases: case 1, case 2, case 3. The first cases is in this 4 location, this 2, and the other one, the case 3 is at the centers. How does it behave? We have done a simulation on this. You look at case 1 and case 2. This is how the case 1 will look like. That means you put the piezoelectric more on the side, and this close to the center actually. That's how it crosses. And this one is case 2 is at the center, and case 2 is at most between center and the side actually. So the conclusion is case 2 is the best. I mean, if you consider first mode and second mode, you place the sensor at the not too far away from the center and not too far away from the edge. That is the best control for the effect actually. Okay, how about flutters? When you subject to airflow, when we have a plate. So we study in such a way, we put 2 piezoelectric material on top and bottom. And we study the effect of that. First, we pick FGS is a stronger plate so far, as what we know actually from our study. So we subject to different temperatures where aircraft flow, they will be increasing in temperature actually. We study 0K, 200, 400K, all the way down actually. So the conclusion now is when increase the temperature, they reduce the air elastic stability. That means it's less stable of the structures actually for this kind of FGCNT plates. When you expect the aspect ratio, then how about the thing getting longer? So you look at the thing is, the aspect ratio increase, the flutter bounce also increase actually. All of them increase in the flutter bounce. This is a study. If you put the piezoelectric full, this is top and bottom full piezoelectric fill out actually. This is we put partial of that piezoelectric materials actually on that, and this is how the result will look like. If you put a full one, I think you see the after bounce. and you look, the inner part actually. When you optimize it, then you get a better control because it's shortened back and the range is bigger for you to make control on that. This is a picture actually. You look at, if this is the optimal presence of this piezoelectric. So this is how the bounce is bigger. Actually, it's easier to do the further control. I'm not going to talk. I think the time is about up. Actually, I prefer to have more questions actually. And now this is some of the research funding, and I have a big research group. I have about 20 students so far working in the group, and thank you. I'd like to have any questions? It's very similar to it's very similar to composite materials. And you look at carbon nanotubes actually. When you replace the glass fibers with carbon nanotubes, you see carbon nanotubes even better. I would say it's even better because I think my colleague later will present in other papers. I think when you have the carbon nanotubes actually, the stick to the matrix is much better than the glass fibers. One. And the corrosion is no different from, when you replace by carbon nanotubes. There's no different from that in terms of corrosion. Yeah.
Thank you for my talk. The theoretical calculations. So have you tried to do with the experience? Experiment.
Yes.
Have you tried to do it?
I have to say it's not easy to do experiment, and we are looking for a partner actually. We are working actually on the partner to work on that actually.
Okay.
They are experiment.
Okay. And the second question, what type of piezoelectric you use in the calculations?
Just a normal type of piezoelectric.
What type of piezoelectrics? It's a PZT or?
PZT.
Okay.
Yes.
And even is the thin film or ceramics?
Thin film.
Okay.
Yes.
Yeah. Thanks.
Okay, thank you for the nice talk. You were discussing about the reason why the double wall or nanotube will fail, why the single wall will not fail at the same temperature.
Yes.
Apparently, the single wall resists a higher temperature than the multi-wall, and the reason was that the inner tubes vibrate and collide with the external tube.
Yes.
And my question is this: what happens to the external tubes when the inner tubes are vibrating? Are they not supposed to vibrate at the same time? That's my first question.
Yes.
The second question is I'm more interested in this plastic deformability of carbon nanotube. Have you done any work on that?
No, I don't. I don't work on that. Okay, for the first question, when you have a single nanotube, actually, when we vibrate, it's free to vibrate with the wall, actually, we don't hit on that. Can you imagine when we have two walls, when usually they are in phase and out of phase, actually. When you have in phase, they both move in this direction, that's fine. That's not a problem. If the outer one moves in this direction, internal move in this direction, what will happen? Collision. That's happened actually in that part. So it collides. So it is failed earlier. There's the reason behind that. Okay. I hope so.
Thank you very much indeed. At the beginning, you mentioned all your experiments or maybe the samples even on bending at the ends. What about shear stress? Have you considered this at the ends? Maybe there's some shear and maybe they have an effect on the other properties. Thank you.
That's a good question. We don't do that actually, because what we do is we do a pure bending. We simulate as a pure bending. It's not easy to simulate with the shear and the bending actually at the same time. It's not easy by MD simulation. The computation time is too large on that kind of simulations. But we did not do that.
Thank you very much.
Yeah.